So here we're going to use another diagram from Klein and Dutro. This is from their chapter 12, and it illustrates the issue of order-disorder. This is a different kind of transformation compared to two others that we've discussed in other videos, displacive and reconstructive. We can also call this perhaps a third-order transformation compared to reconstructive, which is a first order, and then displacive, which is second order. So what is order disorder? Well, this diagram down here illustrates this perfectly. So aluminum and silicon can both go into tetrahedral sites. We could write a little superscript Roman numeral 4 here. Both of them can go into a tetrahedron. So we have an atom that is in the center of this fellow here. This is bonded to 4 oxygens, and usually we just show it by showing the tetrahedron itself instead of the atoms. So we can put an aluminum in there, which has a 3 plus charge, or we can put a silicon atom, which has a 4 plus charge. Now there are some other charge balancing issues that must be taken care of if we're going to make a substitution of aluminum for silicon or vice versa. And we have a video where we take a look at coupled substitutions in our solid solution YouTube video. And we look at the feldspars. But here we're going to ignore the charge balance stuff. That's taken care of sort of off the screen or out of view. And we're just going to look at the tetrahedra themselves. So let's say we have 4 of them. So there's 4 tetrahedra here. And this shows a twofold rotational axis that goes in between these two. So these guys are pointed up, and then these fellows with the dashed lines are pointed down. And then if we swing these around along this axis, so we turn them in this direction, swing them around 180 degrees, then these fellows would be up here pointing up, and then these fellows would come and swing down, and they'd be pointing down. So we have some twofold rotational symmetry in this case here. What does the 1/4 mean? It means that if we're going to take 4 different sites, and we're only going to put aluminum in one of them, so aluminum is 1 out of the 4 sites, then by definition, of course, if all are filled, then silicon will occupy 3 out of the 4 sites. This 1/4 is really talking about the chance of seeing an aluminum. If aluminum can go on any particular site, let's say it does so randomly, then we might have an aluminum here or there or there or there. We would have an equal probability, a 1/4 or 25% chance of seeing aluminum in any of those sites. So aluminum, if we look at millions upon billions upon trillions of sites within a crystal, it will be roughly equally divided amongst these 4 sites. And then if there's a 1/4 chance of seeing aluminum in this particular fellow, then by the same token, there'd be a 3/4 chance of finding a silicon in that site. All right, so let's take a look at these other cases. So this is case A over here. What's going on in letter B? So in letter B, we have instead aluminum only occupying these sites on the right-hand side. So aluminum will go here or here, but not over there and not over there. These will be filled with silicon, not with aluminum. Now, why would that be the case? Well, aluminum and silicon are not the same size. If there's a little bit of a difference in the sizes of these, or maybe there's a charge balance issue, maybe there's a large potassium atom sitting over here that wouldn't normally be there, and it provides some charge balance by keeping the aluminums over on the right-hand side, then aluminum might have either a structural or a charge balance preference for being over on the right-hand side. And if that's the case, if we're going to fill in 1/4 of the sites with aluminum, but out of those 4 sites, only 2 of them are available, now we have a 50-50 chance, a 1/2 probability of seeing aluminum either here or there. So let's say there is a charge balance issue and there's a large potassium atom sitting off over here, but nowhere else in the structure. Then we can have case C. So that means that aluminum might actually prefer this site over all the others, and we would have a 100% chance, a probability of 1, of seeing aluminum in that upper right site. And the chances of seeing it in any of the other sites would be 0. And so that means we would always find aluminum over here and never over here. So if 1 out of the 4 aluminums, sites is filled with aluminum, it would always be the case that we'd have silicon, silicon, and silicon on those sites, and then aluminum up there. This is a fellow that has order, and this is the fellow that has disorder. And this guy is just kind of in between. So B is a case that's intermediate. It's got a little bit of ordering. Ordering is important because it often happens at low temperature, while disorder happens at high temperature. If we have a very high temperature system, then it's easier for these atoms to bounce around from one site to the next to the next. And so we would expect more of a random scattering and kind of an equal probability of finding that aluminum atom in any of those sites. But if we have a very cold system, there's a little bit less energy to push aluminum over some activation energy barrier that might allow it to occupy one of these other sites. And so with less energy and less incentive for it to move around, it's just going to stay right there and charge balance the potassium or whatever else is going on over here. So that's the case of order disorder. Probably the single biggest application is these are very important as thermometers. We can use order disorder relationships in various kinds of phases to tell high temperature or low temperature systems. Actually, it's not just making a category, but we could have a continuum of order from, let's say, high to low, and that would be a continuous thermometer that would tell us how hot or cold a certain geological system is.